When we think of nuclear chemistry, our first thoughts may be of nuclear power, atomic bombs, and weapons of mass destruction. True as this may be, it is also true that nuclear chemistry and the use of radioactive elements have become invaluable tools in all areas of science. Nowhere is this more important than in nuclear medicine. That is, in the use of radioactive isotopes as tools for both the diagnosis and treatment of diseases. To describe the full range of medical uses of nuclear chemistry would take far more time than we have available in this course. What we will do instead is to choose several examples and illustrate the range of applications of nuclear chemistry to the health sciences. So here, the learning goal is to describe the general use of radioisotopes in medicine. Radioisotopes with short half-lives are used in nuclear medicine because chemically and metabolically a radioactive isotope behaves the same way as a non-radioactive isotope of the same element. Once incorporated into cells, the radioactive atoms are detected because they emit radiation, giving an image of an organ. So here in table 5.8 lists the different medical applications of a variety of radioisotopes. So a common factor is that these radioisotopes have to have a short half-life. Let's look at iodine-131. This is a beta and gamma emitter with a half-life of 8.04 days or 8 days. It is used to image and diagnose a malfunctioning thyroid gland. The thyroid gland in the neck produces a hormone, thyroxine, which controls the overall rate of metabolism, use of food in the body. One molecule of thyroxine contains 4 iodine atoms. When radioactive iodine-131 is injected into the bloodstream, the thyroid gland takes it up and incorporates it into thyroxine. A normally functioning thyroid absorbs about 12% of the administered iodine within a few hours. An overactive thyroid, hyperthyroidism, absorbs and localizes iodine-131 in the gland much faster, and an underactive thyroid, hypothyroidism, does so much more slowly. By counting the gamma radiation emitted from the neck, one can determine the rate of uptake of iodine-131 into the thyroid gland and diagnose hypothyroidism or hypothyroidism. So here's a continuation again of the radioisotopes that are used in medicine. Let's do a learning check. Which of the following radioisotopes are most likely to be used in nuclear medicine? Pause your video and answer the question. Here you're looking for a radioisotope that has a short half-life. So potassium-40, which has a very long half-life, is not likely going to be used in nuclear medicine. Whereas this potassium-42, which has a half-life of 12 hours, or iodine-131, which we described in a little bit more detail, are most likely to be used in nuclear medicine applications. Medical imaging is the most widely used aspect of nuclear medicine. The goal of medical imaging is to create a picture of target tissue. And to create that useful image, 3 things are required. You need to have a radioactive element administered in its pure form or in a compound that becomes concentrated in the tissue. Right? A method of detecting that radiation is needed, and you need to be able to detect the radioactive source and record its intensity and location. Then a computer is used to process the intensity, location data, and transform it into a useful image. So after the patient receives a radioisotope, the scanner moves slowly across the body above the region where the organ containing the radioisotope is located. And a radiation technologist determines the level and location of radioactivity emitted by that radioisotope. For example, gamma rays that are emitted can be used to expose a photographic plate and produce a scan of that organ. So before, when we talked about iodine-131, this shows you the accumulation of that radioisotope in the thyroid. And if you have a overactive thyroid or hyperthyroidism, you have accumulation very rapidly. Whereas if you have hypothyroidism which is an underactive thyroid, accumulation occurs much more slowly. Another type of medical imaging is called positron emission tomography, or PET. This method is based on the property that certain isotopes, such as carbon-11 and fluorine-18, emit positrons. Positrons have very short lives. When a positron and an electron collide, they annihilate each other, resulting in the emission of 2 gamma rays. Because electrons are present in every atom, there are always lots of them around, so positrons generated in the body do not last very long. So positron emitters with short half-lives are combined with body substances such as glucose. Glucose has the formula, and we'll see this in later chapters, C6H12O6. For PET scans, one of the oxygens is replaced with a fluorine-18. You create fluorodeoxyglucose, or FDG. And FDG is administered intravenously, and this tagged glucose soon enters the brain and other tissue, and gamma rays are produced and detected, and we can pick up the signals that come from the areas where the tagged glucose accumulates. So this allows us to study brain function and metabolism and blood flow throughout the body. So here, if we look, we have our positron emitter, our fluorine. Okay, it emits a positron, and then that positron is going to combine with an electron to give us 2 gamma rays, and I'll show you that here. So there's my positron plus my electron, and they combine to give 2 gamma rays. And so in PET scans, you are detecting the emission of these gamma rays. Although we haven't learned about metabolism yet, all cells use glucose for energy. In particular, cancer cells, because they're rapidly dividing, use lots of glucose. So cancer cells take up these FDG, these positron-emitting glucose molecules, very quickly. And so in a PET scan, when you have cancer cells, they show up as these hot spots where you have lots of FDG accumulating and lots of gamma rays being emitted. Like conventional X-rays, computed X-ray tomography, or CT, uses X-rays to create images, but with a circular array of detectors that surround the body. The information from the detectors is downloaded to a computer for processing to create a 3D image. CAT scans can be used to diagnose brain hemorrhages, pneumonia, appendicitis, complex fractures, and lung cancer. So based upon the density of tissues and fluids in the organ, the difference in absorption of these X-rays provides a series of images of the organ. Magnetic resonance imaging, or MRI, is an imaging technique that does not require X-ray radiation. X-rays have several drawbacks for medical imaging. X-rays cause adverse biological effects on cells with which they come in contact due to their high energy radiation. As such, exposure of both the patient and an X-ray technician must be limited. Moreover, because disease or damaged tissue often yields the same image as healthy tissue, X-rays frequently fail to detect illness or injuries. MRI has none of these disadvantages of X-rays. Diseased tissues appear noticeably different from healthy tissue, and the use of radiofrequency radiation in MRI is not harmful to humans in the doses used. And you can see it's one of the least invasive imaging methods available. So certain atomic nuclei have a property known as spin. We didn't get into the discussion of electron spin when we looked at Chapter 4 and looked at the properties of atoms and elements. But the spin of electrons is responsible for the magnetic properties of atoms. Spinning nuclei behave as tiny magnets producing magnetic fields. MRI is based on the absorption of energy when certain nuclei are excited by a strong magnetic field. Because hydrogen is a major constituent of aqueous body fluids and fatty tissue, the hydrogen nucleus is the most convenient one for study by MRI. Recall that the hydrogen nucleus has one proton and one electron, and there are two possible spin states, either positive or negative. Again, we didn't discuss these spin states, but there's a spin up state and a spin down. And there's only one proton and one electron that we have to deal with hydrogen. In the presence of an external magnetic field, a spinning nucleus can align itself either in a low or parallel energy state or a higher anti-parallel energy state. Remember when we looked at electromagnetic radiation and we looked at the absorption of energy? So your lowest energy state is the ground state. And when exposed to some type of energy, we can promote or go to a higher energy state. So here we are looking at the absorption of radio waves in the presence of an external magnetic field. So once this energy is absorbed, that change, that excitation, can be measured by these stimulated nuclei. And that change is going to be correlated to the environment in the body. So because the chemical environment of a tumor is different than the chemical environment of a healthy cell, different amounts of energy or different quantities. Remember, in order to excite, you need to have quantized energy. Right? That energy is going to be different if that hydrogen is found in a tumor or if it is found in a healthy cell. So these energies can be calculated and converted to give you a three-dimensional image of the body. You do not have to know the intricacies of MRI imaging. I just wanted to give you a basic level of understanding of what's happening when you get an MRI.